Hello and welcome to Jeremy's IT Lab. In this video, we'll continue our discussion of OSPF neighbor relationships from the previous video, this time focusing on authentication. OSPF authentication helps protect the network from unauthorized devices or attackers trying to inject false routing information into the OSPF domain. Let's get started. In a secure network, you don't want your routers forming OSPF neighbor relationships with unauthorized devices. That leaves your network vulnerable. There are two main ways to reduce the risk of unauthorized adjacencies: passive interfaces, as we saw in the previous videos, and authentication. In this video, we'll look at the second method. OSPF v2 authentication-related information is contained in the common header used by all packet types. We saw this in the previous video. The authentication type field indicates what type of authentication is being used. There are three types. Well, type 0 isn't really an authentication type. It means null authentication. In other words, no authentication. This is the default, so if you don't configure authentication, you're using type 0. With type 0, the router can form neighbor relationships with any device as long as the necessary settings match, the settings we looked at in the previous video. Packets aren't authenticated, and the authentication data field is ignored. RFC 2328 says it can be set to any value, but usually a router will just set it to all zeros. Type 1 authentication is called simple password authentication in RFC 2328. We'll look at it in the next slide, but it's not much better than type 0 because it sends passwords in clear text. If you really want to secure your OSPF domain, you should use type 2, cryptographic authentication, which uses a hashing algorithm to let routers verify the authenticity of OSPF packets. Whichever type you use, a router won't accept OSPF packets with mismatched authentication information. So an attacker won't be able to form adjacencies or inject false LSAs into the OSPF domain. With that introduction out of the way, let's look at how type 1 authentication works, and then we'll move on to type 2. First up, type 1 authentication. Type 1 simple password authentication uses an 8-byte or 64-bit password that is sent as clear text in the OSPF v2 header. And note that 8 bytes means that it can be a maximum of 8 characters, as each character is 1 byte. Here's an example of an OSPF v2 header using type 1 authentication. The authentication type field is set to 1, and the authentication data field carries the password in clear text. When a router receives an OSPF packet, it checks that the received packet's authentication type and password match the locally configured values. And if either doesn't match, the packet is dropped, so an adjacency won't form. So it does provide a basic check, but not much real security. It simply isn't secure, because the password is shown in clear text in a packet capture. Here are a couple of packet captures of hello packets from R1 and R2. Both are using type 1 authentication, and both have the same password configured, so they will accept each other's packets. But you can see the password right here in clear text. If an attacker is able to get a capture of these packets, he can learn the password, which means this isn't a very good form of authentication. Now let's configure type 1 authentication. It's fairly simple, involving 2 steps. First, configure the password on the interface. The command is IP OSPF authentication key, followed by the password. Then, enable authentication on the interface. There are 2 ways to do this. First, you can enable it on a specific interface with IP OSPF authentication. Or you can enable it on all interfaces in an area by configuring area, the area ID, and then authentication under the OSPF process. Let's look at both methods. First, on R1, I used IP OSPF authentication key to configure the password. Then, I enabled authentication directly on the interface. The output of Show IP OSPF interface now says that simple password authentication is enabled. Now let's configure R2. First, I configured the password, but I added a few extra characters at the end. That's not a problem though, because as this message shows, the password will be truncated to 8 characters, so it will actually be the same as on R1. Here's the password in the running config to verify. So, as I mentioned in the previous slide, when using type 1 authentication, the password can be 8 characters at most. If you configure a longer password, it will be truncated to 8. Okay, to finish the configuration, I enabled authentication using the second method, Area 0 authentication under the OSPF process. And like on R1, Show IP OSPF interface says that simple password authentication is enabled. Let's look at an edge case, enabling authentication without a password. If you enable Type 1 authentication on an interface without configuring a password, packets are authenticated using an empty password, in other words, all zeros. Because the authentication type is 1, the router won't accept packets with Type 0 authentication. Let's test. I removed the previous commands from R1 and R2, and then enabled Type 1 authentication on R1 only. As you can see, R1's neighbor table is empty. To see why, let's look at some packet captures. Here are the hello packets that R1 and R2 send. Notice that R1's header specifies Type 1 authentication, and R2 specifies Type 0. Because these don't match, they don't accept each other's hellos, so they don't become neighbors. Wireshark displays the authentication data a bit differently, but they're actually the same. Both are just 8 bytes of all zeros. However, the authentication types are different, so the packets still don't match. You probably won't ever enable authentication without configuring a password, but just keep in mind that both the authentication type and the authentication data, the password, have to match. If one of them doesn't match, the router will drop the packet. Now let's move on to Type 2, cryptographic authentication. Type 2 uses a hash function on a combination of the OSPF packet and the configured password or key to generate a digest. The digest is then sent to the neighbor, not the password itself. Here's how the OSPF v2 header looks when using Type 2 authentication. Notice the digest at the end. This isn't a cryptography course, so we won't get into how hashing works here, but you can think of it as a one-way mathematical function. A hash function takes some data and converts it into a fixed-length value called a digest, sometimes simply called a hash. This process is designed to be one-way, so even if an attacker does a packet capture and learns the digest, he can't derive the key from the digest alone. Let's see how it works. R1 takes the OSPF packet and the configured key, and runs them through a hash function such as MD5, resulting in a digest. This digest is then appended to the OSPF packet and then sent to R2. Now, how does R2 verify that the packet is authentic? The receiver, R2, then performs the same calculation using the received packet and its locally configured key. If the newly calculated digest matches the digest in the packet, the receiver accepts the packet. If it doesn't match, it drops the packet. This process is much more secure than Type 1 authentication, because the configured key is never sent to the neighbor, only the digest is. And there is also a sequence number included that helps protect against replay attacks. This sequence number must be non-decreasing, so if an attacker tries to send an old packet, it will be rejected for having an old sequence number. Here's a packet capture of hellos between R1 and R2. Let me point out a few things. First, the key ID shown here is used by the receiver to identify which configured key to use when it verifies the received packet. As you'll see in the next slide, you have to configure a key ID for each key. The receiving router must have a matching key configured under that same key ID, or it can't verify the packet. Next, notice the auth crypt data length, in this case is 16, because I'm using MD5 as the hash function, and MD5 creates a 16-byte digest. Next, note that each router maintains its own sequence number for the OSPF packets it sends. So R1's and R2's sequence numbers are independent, but they do track each other's sequence numbers. R1 remembers the last sequence number it received from R2, and R2 remembers the last sequence number it received from R1. Finally, we have the auth crypt data, which is the digest. Notice that each router's digest is different, even though they are using the same key. This is because the OSPF packets aren't identical. For example, the source OSPF router in the header is different for each router. Both the OSPF packet and the key are used to calculate the digest. So even with the same key, these routers send different digests. And finally, notice that the key itself isn't visible in the packet capture. It's only used as an input to generate the digest. This is much more secure than sending it over the wire, like in Type 1 authentication. Now let's look at how to configure Type 2 authentication. There are two ways to do it: legacy configuration and keychain configuration. Let's start with the legacy configuration. Note that legacy isn't an official name or anything. It's just what I call it since it's the older method. First, configure the key, the password, on the interface. The command is IP OSPF message digest key, followed by the key ID, MD5, and then the key itself. Note that this legacy configuration method only supports MD5. If you want to use a stronger hashing algorithm, you have to use keychain configuration, which we'll cover after this. Anyway, after configuring the key, you have to enable authentication on the interface. You can do that on a specific interface with IP OSPF Authentication message digest. Or you can enable it on all interfaces in an area with area, the area ID, authentication message digest under the OSPF process. Let's configure Type 2 authentication on R1 and R2. On R1 first, I configure the key with IP OSPF message digest key, a key ID of 1, MD5, and then the key. And then I enabled Type 2 authentication with IP OSPF Authentication message digest. This time, Show IP OSPF interface says cryptographic authentication enabled and also identifies the most recently configured key ID, 1. Now let's configure R2 side. First, I configure the key with the same command as on R1. This time, I enabled Type 2 authentication on all interfaces in Area 0 with Area 0 Authentication message digest. And the output of Show IP OSPF interface is the same. Now, before we look at the keychain-based configuration method, let's focus on this part of the command, the key ID and its purpose. Periodically changing cryptographic keys is a common practice, and this is called key rotation. But of course, the process should be done smoothly without interrupting the network. The OSPF key ID, which we configured in the previous slide, allows for multiple keys to be configured at once. This facilitates key rotation without dropping the adjacency. And this is enabled by the rollover process during migration. Let's see how it works with an example. R1 and R2 are currently using key 1, which I configured in the previous slide, but we have to migrate them from key 1 to key 2. Here's how we can do it without interrupting the network. First, configure the new key 2 on R1. Then do the same on R2. Finally, after both routers are using key 2, remove key 1 from R1 and R2. Let's try it out. I configured a new key with key ID 2 on R1. So currently, R1 has keys 1 and 2 configured, and R2 has only key 1. Here's the output of Show IP OSPF interface on R1. I want to point out two important things here. The output now says youngest key ID is 2, because it's the most recently configured key. Remember that. The youngest key is the most recently configured key, but not necessarily the one with the highest key ID. If the first key had key ID 100 instead of 1, key 2 would still be the youngest because it was most recently configured. But here's the real important point. Rollover in progress, one neighbor using the old key, key ID 1 algorithm MD5. So because R1 has identified that R2 is still using the old key, R1 has initiated a rollover. If the router identifies that any neighbor on the interface is still using an older key, it will initiate a rollover. So that means that after step 1 in the migration process here, R1 initiates a rollover, as the command output shows. And what exactly does a rollover entail? The router will send duplicate OSPF packets, one with each configured key. Here's how it looks in a packet capture. Notice the pattern. R1 sends 2 hellos, R2 sends 1. R1 sends 2 hellos, R2 sends 1, etc. Each of these hellos from R1 uses a different authentication key. One uses key 1 and one uses key 2. R2 only has key 1 configured, so it only sends hellos with key 1. The point is to enable a smooth transition from key 1 to key 2. During this rollover, R2 accepts the packets with key 1 and drops the packets with key 2. But after we configure key 2 on R2, it will accept the packets with key 2, and R1 can stop sending packets with key 1. So neighbors using the old key accept packets with the old key, and neighbors using the new key accept packets with the new key. This is a point-to-point connection, so R1 only has one neighbor, R2, but it could be a broadcast network with many routers connected. This rollover process lets them all maintain their adjacencies as you migrate to a new authentication key. Let's finish the process by configuring key 2 on R2 now. I configured key 2 on R2 with the same command as R1. Make sure the key ID and the key itself match. Here's the output of show IP OSPF interface. It says youngest key ID is 2, as expected. And here is G1's running config. I haven't deleted key 1, so both keys exist on R2 G1 at the moment. Let's take a look at R1 side now. This time, show IP OSPF interface doesn't say anything about a rollover. It just says youngest key ID is 2. But just like on R2, key 1's config still exists. But let's look at the packet capture now. Instead of sending 2 hellos at once, R1 is now sending only 1 hello, and that hello uses key 2. After both routers are using the youngest key, key 2, R1 stops the rollover process and stops sending packets with the old key, key 1. And it is now safe to remove key 1 from the configuration. So that's the purpose of the key ID. Throughout this process, R1 and R2 never lost their adjacency due to mismatched authentication keys. The key ID makes authentication key rollover possible, letting you migrate to a new key without disrupting OSPF operation. For the final topic, let's look at how to configure OSPF authentication using keychains. A keychain is a list of authentication keys, each with a key ID, a key string, which is the key itself, and a cryptographic algorithm. And multiple algorithms are supported, not just MD5. Here are the basic commands you need. First, create the keychain with keychain and then a name. Then create a key with key followed by a key ID, which is a number like we saw before. Then configure the key string with key string followed by the actual key, the password. Then specify the algorithm with cryptographic algorithm followed by the name of the algorithm. Here are the options on the CSR1KV routers I'm using in CML. Notice at the bottom that MD5 is also an option. In fact, if you use MD5, keychain authentication is compatible with legacy configuration. So you could have R1 using a keychain and R2 using the legacy configuration we just covered. But these days, MD5 isn't considered very secure, so it's best to use one of the HMAC SHA options. Finally, apply the keychain to an interface with IP OSPF Authentication keychain, followed by the name of the keychain. Note that, when using keychain authentication, there is no command to enable authentication on all interfaces in an area. You have to use this command on each interface. And that's it. In addition to allowing more secure algorithms, keychains also make key rotation easier by allowing you to specify the lifetime of each key, but we'll look at that later. First, let's configure basic keychain authentication on R1 and R2. I'll start with R1. First, I created a keychain named OSPF. Within that keychain, I created key 1. Then I configured the key string, ENCOR, and then specified HMAC SHA 512 for the cryptographic algorithm, which creates a 512-bit digest. The final step is to apply it to the G1 interface with IP OSPF Authentication Keychain, OSPF. And here's the output of show IP OSPF interface. Type 2 cryptographic authentication is enabled, and it's sending key 1 in the keychain OSPF. And I used the same commands to configure R2 as well. As you can see here, R1 and R2 were able to establish an adjacency. You can use show keychain to show any keychains configured on the device. Notice the part I highlighted, referencing the accept and send lifetimes. Since I didn't specify any lifetimes, these keys are always valid. But if you want to migrate to another key, you can configure these lifetimes to make that process more automatic. Let's see how to do that. With keychains, you can configure date-based key rotation. Each key in a keychain can have a send lifetime and an accept lifetime. The send lifetime is when the router uses that key to send OSPF packets. You can configure it with the send lifetime command. The local keyword means the router should use the local time zone configured on the device. Start is a time specified in hours, minutes, seconds, day, month, year format. For end, you have a few options. You can specify a duration in seconds, or infinite if you want it to be valid forever, or a time in the same format as the start time. I'll show an example in the next slide. The accept lifetime is the period the router accepts OSPF packets signed with that key. The syntax is basically the same as the send lifetime, but the command begins with accept lifetime instead. For both of these commands, if you don't specify the local keyword, the times are treated as UTC. During migration, it's best to have some overlap in these times to allow for a smooth transition without dropping the OSPF adjacency. Let's look at a concrete example so you can see how these commands work. For our example, key 1 should be used from January through March, and key 2 should be used from April through June. But let's leave a bit of overlap as a safety measure. For key 1, the send lifetime is from midnight on January 1st until midnight on April 1st. But for the accept lifetime, I extended it by an hour until 1 a.m. on April 1st. And then for key 2, the send lifetime starts at midnight on April 1st and ends at midnight on July 1st. But the accept lifetime is until 1 a.m. on July 1st, leaving some overlap for the next key in the rotation. So there's a 1 hour window of overlap from midnight to 1 a.m. on April 1st to transition from key 1 to key 2. During that time, the routers will accept either key 1 or key 2. If the router's clocks are perfectly synchronized, an overlap might not be necessary, but a short overlap like this is a good safety measure. Exactly how you configure these overlaps and how long they are is up to you, but it's generally a good practice. So, by using send and accept lifetimes, you can automate key rotation while helping keep the OSPF adjacency up. Here's a review of the main points from this video. Type 0 authentication is null authentication. In other words, no authentication, the default. Type 1 is simple password authentication, which sends the password in clear text for authentication, which is not secure. Type 2 authentication is the correct choice, as it uses a hash function to generate a digest, which can be sent instead of the password itself. We covered 2 ways to configure it. Legacy configuration supports MD5 only, and keychain-based configuration supports a variety of hashing algorithms, and also supports date-based key rotation by specifying the send lifetime and accept lifetime of each key. Now let's do a short quiz to test your understanding. Here's quiz question 1. Which of the following statements about Type 1 OSPF authentication is true? Pause the video now to think about the answer. Okay, the answer is B. It sends the password in clear text. Type 1 is simple password authentication, and as you can see in this packet capture, it sends the password in clear text, so it's not secure. It doesn't support MD5 or key rotations with send and accept lifetimes, and it's also not enabled by default. The default setting is Type 0, which is no authentication. Here's quiz question 2. R1 and R2 are using the legacy OSPF Type 2 authentication method with key 1. What happens after you configure key 2 on R1, but not R2? Pause the video now to think about the answer. Okay, the answer is C. R1 sends duplicate OSPF packets, one with each configured key. When R1 sees that a neighbor is still using an old key, it will initiate a rollover, sending duplicate OSPF packets, one with key 1 and one with key 2. If you then configure key 2 on R2, R1 will end the rollover and only send packets with key 2. Here's quiz question 3. When configuring Type 2 authentication with a keychain, how can you apply the keychain to an interface? Pause the video now to think about the answer. Okay, the answer is A. IP OSPF Authentication Keychain. The message digest command is used for legacy authentication configuration without a keychain, so B and D are incorrect. And when using keychains, there is no option to enable authentication on all interfaces in an area, so C isn't a valid command. Okay, that's all for the quiz. And that's all for this video on OSPF authentication. We covered simple password authentication and cryptographic authentication with both legacy configuration and keychain configuration. By configuring authentication, you can secure your OSPF domain and ensure only the intended routers can become neighbors. I hope this video was helpful. Thanks for watching. Before we wrap up, I want to say a quick thank you to the channel members whose names you see on screen. Your monthly support helps me keep making these videos and keep this content free for everyone on YouTube. I really appreciate it. Thank you for your support. If the video was helpful and you want to support me, click the join button under the video. And please subscribe and like the video. It really helps me grow the channel and keep making these videos for you all. Thanks again.